All right. Okay. So the marks for your programming test and also written test have been released. Just about your programming test. So for tomorrow, for your lab session, you don't need to go to your enrolled session. You can go to either one. Okay. So Shamru, one of our lab assistants, he will be there. And then he's actually going to be ready. If you want to maybe look at your feedback file, you want to compare that against maybe your submitted rodent specification. If you want to take a look, he can maybe show that on his screen and give you some feedback. So it's completely up to you. It's provided, for you, if you want some feedback. We'll try to see how the request might be. If there are too many of you really want to see that, that's completely fair. In which case, I still have 2 more hours that I can supply. So we'll see how that goes. So, okay. So tomorrow, please just make sure you go. You can go to the 1:30 session. You can go to the 2:30 session. You can go either way. Sharon will be there with glasses. All right. All right. He'll be there. And then your lab number 3 also has been released. So please take a look. And that one there is just going to be about approaching the celebrity problem in a slightly different way. So you will learn some stuff from there. I will mention one of the useful syntax to you also maybe a little bit later in the lecture, but please get busy with that. And then we got, after lab number 3, we got one more lab. And that lab, I promise, no more celebrity, right? So something different. That's gonna be something useful to actually take a look. That will be the last lab. I believe your exam schedule has been released. I think our exam, I forgot exactly which day, but what we can, sorry? 11th of December. Okay, I'll take your word for that. Okay, so I think what we will try is after our very last class, we can schedule maybe some exam review session for everybody. We can see either over Zoom or maybe in person. We'll see how that goes. Right? I'll reach out to you guys about it. Any question about the course? I'll take it here.
What's the average mark for written exam? For this written test, not the exam.
Written test 1? Oh, I mentioned that. It's 55.
55.
Yeah,
right.
55.
All right, thank you.
Can you see that on the E-class? I guess you cannot, right?
You mean in the announcement?
I think in the announcement I mentioned it's 55.
Oh.
If I didn't, okay, on the E-class anyway, right? But it's 55, no secret.
Thank you.
Yeah, question?
Where can we find the programming test? Where I can't see it on my emails?
You mean, if you want to see the programming test marks and also feedback file, please take a look at the announcement. I think for the marks for your programming test, you have to look at the ePost link. That one will require your EECS login. And then for the feedback, you'll have to log into some terminal on the remote lab and then type some command, like a feedback 3342 and then proc test 1, something like that, right? Give it a try. If it doesn't work, let me know. I'll fix it. All right, good. Guys, any other questions? All right, so good news. At this point, no more programming test. So we just got one more written test too. Okay, and then we got exam. So my advice for you would be, I think since it's December 11th, right? Still about more than a month away. I would say you can maybe try to kind of urge yourself, maybe about a month away from the exam, you may want to start going through all the materials in the course, since it's going to be a cumulative exam. I would tend to guess your fellow student in the previous year, they didn't do as well in the exam, maybe because they got too many exams to really get prepared at the same time. So they didn't really get to devote too much time, for each one of them. So please do go through the material, form some study group. Really, that's really what I recommend. I'll give you some example questions, but again, they are just examples, right? Anyway, if you got any concern, do speak to me. My apology for the cancellation yesterday for office hour, but I will be there tomorrow if you want to speak to me. Okay, let's do some quick recap, and then we'll cover some stuff. All right, so yesterday, sorry, not yesterday, I meant last week. Last Thursday, we were talking about using the formal components. We talked about our very first proof obligation rule. Just remember each proof obligation rule. Use all the symbols that we kind of spoke about in the formal component slide, right? You don't really have to memorize them, for your exam. You can feel free to either include a proof obligation rule or just include any example you like in the data sheets. But this one here, we figure out is going to correspond to 2 times 2, 4 sequence. So each one of them you can think about is going to be instantiated from this particular proof obligation rule. How do you figure out the number? We'll see one more example. We'll see another 1 or 2 examples today. Look at this. So whenever you want to look at, of course, you got to understand the meaning for each component here. So A here means all the axioms collectively. So there's no variation, just all the axioms. I here means all the invariants in the pre-state, also no variation. And this is the first point of variation. It's about the guards for a particular event. In that case, since we got two events, so there are two possibilities over here. And then for here, the subscript I means about the index of the event. Since we got 1 or 2, we got another 2 variations. So 2 times 2, right? That's how we figure out. So we'll see some other example as well, just about how many sequence can be instantiated from the proof obligation rule. We'll see. And then we just kind of did some exercise together about understanding the naming convention, right? And then we try to, in the next page, we try to formulate each of the proof obligation, as a sequence. So please just remember, I'm pretty sure once you follow through all the definition here, it's very easy usually to follow all these. It's really the goal over here that's going to be a little bit trickier, because the goal over here, in this case, talks about a particular invariance in the post states. For example, let's say when we talk about invariance 0, 1 over here. So if you simply put n is a member of natural number, that's not exactly correct because it's not a post states. So we want to first of all change n to be n prime. So that's a post states. However, n prime itself is also not correct either. You have to somehow replace the prime by the corresponding before after predicate, which will correspond to n plus 1, right? That's kind of the steps we follow. We're still going to keep doing this exercise here, but just make sure you pick it up at some point. You will need that for written test 2 and also for the exam for sure. All right. So if you got any trouble understanding about exactly how to figure out the invariance in the post states, let me know. Okay, we can still go over. And then, okay, syntax semantics. So there are only 2 syntax we'll need for the bridge controller, right? Just like a mathematical notation. We need a sequence and also need inference rule. So okay, let me just go to here directly for the comparison. Whenever you talk about sequence, like what we did earlier, you can either vertical or horizontal. Oh, sorry, let me do it again. Either it could be vertical right here, or it could be horizontal like that. Okay? Usually, when you see the inference rule, the sequence there above or below the horizontal line is usually presented horizontally, usually. And sequence simply refer to some implication, which will be subject to proof. You may or may not be able to prove it. We'll see cases today, okay, very soon. However, for inference rule, first of all, you got some name. What's the rule, the name of the rule? And then we got antecedents, we got consequence over here. Whenever you're given a rule, especially the rules that we're going to talk about in the class, they will be considered as axiom, meaning that you don't really have to prove it. You can just assume they are true. However, today I'm going to show to you some little exercise. If you're really kind of questioning about why is this a rule, you can actually try to prove it, right? It's still boiled down into the kind of the proof we talk about in the predicate and propositional logic that we did in math review, right? Everything will get connected somehow. Right, so please make sure you get very clear about sequence versus inference rule. We'll put it this way. In the case of the sequence, it's just alone. However, in the case of the inference rule right here, A here, antecedents, and consequence C here, both of them will contain a set of sequence. So inference rule uses sequence, but not vice versa. All right, that's another way to see it. All right, and then we talk about the steps and structure for. Usually the sequence proof will do more. Maybe not a very complicated one today. Maybe once, let's see, hopefully today we can get into maybe deadlock freedom. We'll do some introduction, but the proof about deadlock freedom is going to be very interesting. We'll do it from scratch altogether, just to let you see, get a feel about what a long sequence proof might look like. So usually this is the structure. You start with something, a single goal, and lots of hypotheses. Typically, the very first step is to apply the so-called monotonicity rule by dropping all the irrelevant hypotheses. So let's say I only consider 1, 2, and 3 to be relevant or useful for my proof. So I'm going to keep them only. So usually after you dropping the hypothesis, you got to make sure you connect the sequence over here and the sequence over here using monotonicity. All right. Once you do that, you can now apply for as many inference rule as you like. Just remember, ultimately, you should really say, now the proof is completed because the very, very last sequence I have simply match some axiom rule, right? That's something we said last time. We'll see more example today, all right? All right, okay, we'll get there, and then, okay, and let's now review this one very quickly, okay? Okay, I think, yeah, that's it. Okay, let's take a look at this rule over here. Let's try to understand this one here, okay? It might look kind of it's all symbols, right? First of all, this means ORL. We have some disjunction that appears to the left of the turnstile. That means to the left of the turnstile, which is here, we have some disjunction. You can think of, which is on the slide, you have some disjunctive hypotheses. Okay, think of that way. And so remember the meaning for the inference rule. In order to prove this, it would be sufficient to prove these. In this particular case, in order to prove this one single sequence, it would be sufficient for us to prove independently this one here and also this one here. Okay, you got to prove these two separately. Presumably, each one of them will be easier to prove compared with trying to prove this one at one go, because you are focusing on just P here and also Q here, right? And let's say a little bit more. So here, if I have some hypotheses, I'm saying I can assume either P or Q. I'm not too sure which one I can assume. So that means I got to split into different cases. In one case, I can assume P. In the other case, I can assume Q. I'm trying to prove the same goal, the goal R right here. All right. Yeah. So please take a look at the correspondence here, which I tried to do last time. Just review that part of the lecture if necessary. And this question here is also very important, right? A here is a correct answer. So we're basically saying, rather than proving one single sequence, we can split that into two sequences. I can also tell you that option B here, to really combine two sequences into one, we will see no cases like that. So we don't really have any inference rule to tell us we're given two sequences to prove. To prove it, we only prove a single sequence. No, there's no such thing. All right. You can later on. You can when you craft your data sheets for the exam, you will see that all the inference rule that we talk about is going to be to prove a single sequence. It will be sufficient to prove either one or two sequence. That's really the pattern. All right. Good. All right. And then okay, guys, any question from last time? All right. Let's now look at another rule, and I want to show you a little bit of justification, just in case you want to kind of dive a little bit deeper into each inference rule. Okay, let's see this one here, for example. So this one here, oh, that's the one we just talked about, right? So here we got ORL, right? Now, let's say you're wondering about why can we do this one here? Why? Okay, so let's see, how do we justify that? So for the purpose of proving, because they have some common hypotheses, let me just remove them. You will see that if you want to add H into the actual predicate proof, it will be easy. But for now, for simplicity, let me just get rid of H, just for now. How do I justify that this rule is actually an axiom? How do I justify it? Let's prove it, right? And we said that to prove this, it will be equivalent to prove these two, right? That's what we're saying, okay? Let me just show to you. So what we want to prove is something like this. So let's now start with this. To really prove this one here, which will be P or Q implies, okay, let me just keep all uppercases, okay. P or Q implies R. It would be sufficient to prove this one here and this one here individually, okay? Simply because that one there would entail this one. That's why it would be sufficient. Just notice the way I put, the consequence and antecedents. Okay, and then, so here this will be P implies R. P implies R. And since I got it separately, so you'll be as if I put a conjunction, right? I got to prove both. It's no option. right? You got to prove both. Doesn't matter which one you try to prove first. All right, and Q implies R. So this is really what the rule is trying to say. And we're saying that this is simply equivalent to, well, the whole thing is equivalent to true. That's what the rule is saying, formally, all right? And let's prove it very quickly. Just, it will require a little bit of the distributivity, implication definition. Let's do that quickly, just a little exercise, okay? So let's now start with the left-hand side. Okay, let me start with this. Okay, so I'm going to write P implies R and Q implies R. And we learned about the definition for implication. And there are two instances, this one here and this one here. Okay, let me write it down. So it's like an equational style, right? So we know that the definition of implication tells us whenever I got X implies Y is equivalent to not X or Y. Right? Think about X and Y, P and R, X and Y, Q and R. All right, let's now write it down. And then, so here we got not P or R, and also not Q or R. All right. Now, let's see how we can go further. You can see that R appears twice in both. Okay. Right? So, if you recall one of the rules, I'll tell you right away. Okay. It's called distributivity of. So, distributivity of or over n. Okay, let's write it down first and then we'll see the correspondence, right? If I have x or y and z, that's equivalent to, if I distribute it, distribute the disjunction over the conjunction, right? If I do that, it's as if I say multiply and then plus, right? You know how to simplify that, okay? That one would be x or y and x or z. All right? You can think about the x over here, and the x over here is like the r here and the r here. Right? And then the y here is a bit like a not p. And the z here is a bit like the not q. Of course, you can actually really swap the order. I'm just ignoring that step, but you see my point. All right? So let's now, using that rule, we can simplify that. So this will be basically r or not p and not q. Right? If you try r or not p, and also r or not q, and then combine with n, right? They kind of work. All right? That's a critical step. And once we get to here, this part here, right? So remember De Morgan, right? Let's now apply De Morgan. Let me make this a little bit smaller, okay? And then we'll complete that in one line. Okay, right here. And if you recall the De Morgan, so we know that if I got not the case x or y, not x and not y. All right? And then you can see that the not x is a bit like the not p over here. Not y is a bit like the not q over here. All right? Okay, let's simplify that. It would be basically r or not the case. P or Q. Okay, follow so far? Okay. And then this one over here, what we can do is, you can think about this falls back to the not P or Q pattern. Not P or Q is really P implies Q, right? So you can think about this part here is a little bit like, think about this one here is X, and this one here is Y, right? Remember we talked about the definition for implication, okay? Final line. So this one will be equivalent to, again, definition of implication. And that one is going to be P or Q implies R. Okay? So P or Q, and we'll get rid of the not. So P or Q and implies R. Right? The definition for implication. I just want to see the correspondence, right? So what we have shown is this. They are actually equivalent, but equivalent simply will entail implication as well, right? It's a double implication. So think about right here, this guy here will be these two. And then this one here is what we have shown right here. They are equivalent. Of course, you can say one is implied by the other. Okay? The actual details for this proof here is not really the focus point. The main point is you can boil down, you can transform every inference rule you're given as like an implication. That if you have any doubts about the validity of the inference rule, you can always try to do some little proof yourself just to see the insights. Okay? All right, any questions? Diego.
What was the argument to not consider H again? That it just appears in all three equations?
Oh, you can think about, yeah, exactly. You can think about if you really have H right here, let's think about what's going to happen. Let's say if you put H back to the place, right? Let me just use laser. You put H, and H back, right? You basically just say H and P implies R. And then you just do H and Q implies R, etc. And then you can still actually do the normal distributive thing as well. It's just that the expression to write will be a little more complicated than right now. So that's why I kind of just get rid of them just for now. Yeah. Good question. All right, so let's now try to look at a little bit more inference rule. So let me see here, right here. So these are the first set of inference rule. I think you got about 3 sets to really know about for this course. So for the exam, you only need to know about the inference rule that we cover in the course, right? That's all you need. Any proof you're supposed to do, those inference rules should be enough. Of course, it's kind of up to you, like which ones you want to put on your data sheets. You can think about, right? Some of them you may not need to. Let's go over one by one, right here. I deliberately use like a green ones over here and red one over here for a reason. Okay, let's go over them. Let's start with the green ones. Okay, so these are so-called base cases. Okay, let's say over here. Oh, actually, you know what? How about this? Let me try that. Okay, and that. And that. Okay, good enough, right? That's the green one. These are so-called axiom rules. Axiom rules. And so these are the base cases of your sequence proof. Of a sequence proof. If you're able to kind of arrive a sequence into one of these, you know that it's proved automatically, right? Right. Let's see the other one, and then we'll go over each rule one by one because it's your first exposure to so many rules. It's better to be more careful. And then the second set is right here, right? So we got right here all these, and these are. They are more like a recursive case, which means you can keep applying, of sequence proofs. Okay, you can see in the axiom one, we just got empty antecedents. But in the case of recursive cases, you got at least one. Here, you got two. All right. Let's look at the axiom rule. I think the P1, P2, P2 prime here, and P3, you may have heard about it, maybe in your math course. It's called the piano number theorems. Just for your reference, I'm going to write it down. So the P here is really referring to the piano numbers theorem. And piano is a mathematician, so just for your reference. But if you just want to remember, it's like a P1, P2, P2 prime, and P3. That's enough, right? All right, so P1. If you have a sequence like this, where you want to prove that 0 is a natural number, it's proved. You don't need to prove it. Automatically proved. Because 0 is a natural number. All right? So that one is easy. How about P2 over here? This is saying, given that n is a natural number, incrementing n by 1, it remains to be a natural number. But not minus, of course. All right? This one here is also easy to see. So to prove this, you only need to prove true. That means you don't need to prove anything. Okay? And this one here is a little bit trickier, a little bit. Okay? Let's try to visualize it. So here, what do we assume? Assumption is n is strictly less than m. Okay? So you can also try to visualize to help yourself a little bit. If I have the number line, n here is strictly less than m. Right? Strictly to the left of m, basically. In that way, if you're trying to add 1 to n, maybe adding 1 to n, the most you can get to will be equal to m. That's what it is saying. For example, if n happens to be m minus 1, in that case, n plus 1 will be just n. But n can also be n minus 2, in which case you wouldn't get to even close to m. Right? If you want, do you need some example? I can do it. All right. So this one here, for example. So for example, let's say n is equal to 2, m is equal to 3. Okay, let's say, right? So we agree that n less than n, 2 less than 3. Good. And now, if I do right here, n plus 1, which is 3, less than or equal to n. True, right? Diego.
Wouldn't you have to assume that both n and m are at the very least part of the integer number set?
It's a very good question here. I think somehow the rule implicitly assumes the type. So you can think about n and m here. They're actually not even natural numbers, just integers. Implicitly, they're integers, yes. Mm-hmm. All right. And then you can also try out other number. Let's say if n is equal to 1, for example here, m plus 1 will be 2, which is still less than or equal to n. Right? So give it a try on that number, right? But this one here is how you interpret that. Just draw a number line, and then you will see. How about this one here? Okay, this one is saying if n is positive, strictly larger than 0. In that way, n minus 1 will still be a natural number, obviously, right? So if you think about, if I know that right here, this is 0. And I know that n is strictly larger than 0. The minimum you will get to will be just 1. In that case, if I say 1 minus 1, I will still get larger than or equal to 0. So I still get a natural number. So think about the different cases. Okay. How about this one here? Okay. This one here will encounter that at some point. This one I would suggest if you got less than or equal to, you can try to split that into different cases. So this means n either strictly less than m or n is equal to m. It'll be easier for you to think about it. All right? So now let's use an example. How about that? for this one here. If I know that n is less than m, so let's talk about case number 1 or case number 2. Now you need to argue for both cases actually for disjunctive assumption. Okay, for case number 1, let's say n is equal to 2 and also m is equal to 3. Right? So now you can see that n is strictly less than m. In that way, if I do n minus 1, n minus 1 is going to give me 1. And 1 is still strictly less than 3, obviously, right? Another one, case number 2. What if n is already equal to m? If n is equal to m is equal to, let's say, 3. In that way, if I try to do minus 1 from n, it's going to be 2. And 2, of course, will be strictly less than m, which is 3. Right? Just use the numbers to see different cases. Okay? Okay so far? Okay? All right, the last one for P3. Given that n is a natural number, then n should be larger than or equal to 0. I think one of your lab zeros axiom actually uses this, right? So that one should be okay too, I guess, right? If it's a natural number, it follows that n should be larger than or equal to 0, okay? All right, let's now take a look at this one we already covered, right? About having the disjunction to the left of the turnstile. That one's already done, okay? So we can skip that one. Now, let's try to look at these two together, all right? This one is saying, so here, this part here about r. The r here simply means to the left, sorry, to the right, beg your pardon, to the right of the turnstile. All right. So to the right of the turnstile, we have some disjunction. So you can see that we have some disjunction here. We have some disjunction here. Both of them appear to the right of the turnstile, right? And then here, the 1 and 2 is telling you if you want to prove a disjunction. That's the goal, not the hypothesis. And it doesn't really matter which one you prove. You can try to prove this one here, or you can try to prove this one here. All right. So think about this one here. P here is really with index 1, and the Q here is really with the index 2. Okay, let me say that again. Okay, to prove this particular sequence here, where the goal is to prove the disjunction between P and Q, P or Q. In that way, it would be sufficient to just argue about P. You can choose the one that you think that's more comfortable or easier for you to prove. You can be selective. And now, again, given some disjunction to prove, I can choose the second one instead if I want to, right? So you have some flexibility. So this tells you if you're given a particular sequence and the goal over there is a disjunction, you don't really have to prove both of them. You can choose the operand that's actually easier for you. Okay. All right, and then let's now look at this one. Oh, monotonicity, right? So we are saying that in order to prove a sequence with H1 and H2 being the hypotheses, we're going to drop H2, which will be the collection of the hypotheses that's now relevant. That's something we said last time as well. Right? So with all these rules, we will be able to argue some interesting property already, but we're going to look at that today in more detail. All right? Questions? All right. And then we can definitely do some exercise together. I'll let you guys think about it. Okay, so let me just do one more thing here, just for you, okay, just to clarify, since I got it on my notes. So let me just copy this about these two. Let's look at these two very quickly, right? Just to visualize that a little bit more for you. So as I said earlier, so think about this P here is more like a R1, okay? And Q here is more like a R2, okay? So this one here, if I apply, be careful here. Let's say I have a sequence right here. If I say hypothesis H entails turnstile P or Q. Now, be very careful. If I give you this as the after sequence, like a follow-up sequence, if I put H over here, and then if I put, for example, Q, which rule did I apply? R1 or R2? Let me ask the question again, all right? This is a one style of the written test question I can tell you, written test 2. Okay, let's practice that together, right? Given this, it would be sufficient to prove this one instead. Which rule did I apply? Did I apply this one here, or did I apply this one here? R2? Because R1 and R2, this is R2, right? Okay, very good, all right. So what I apply is the OR R2, okay? Let's see, what if I apply OR R1? It could be another way I can ask. I can say, now, let's now start with the same sequence over here. And then H, and then I got P or Q. Now I say, apply the OR R1 and give me the resulting sequence. That could be another way to ask. Either I give you the two sequence and choose the rule that I apply, or give you the sequence and apply certain rule, right? Either way. And that one there, of course, we're going to choose R1, which is right here, okay? H or P. Right. Good. All right, let's now see a little bit more. Okay. Okay, I'll talk about the summary a little bit later. Okay, let's now look at the slide very quickly. Okay. So we have talked about all the inference rules. So the slide number 22, 23, all covered. Okay. But you can also take a look at the narrative about each rule. I did put some explanation there. Take a look. I think that they might help. All right, let's now talk about ML out and ML in. Right? If you recall, okay, very quickly, from last time, let me just refer you to what we said last time. So last time, before we spoke about inference rule, we spoke about the 4 sequence that we can generate. So we got this one here, and we got this one here, and we got the other 2, right? 4 of them in total. So now let's put all those 4 sequences related to invariant preservation and try to prove them. Okay, let's now try that. Okay, let's now just go on to all these 4. 1, 2, 3, and 4. Okay, I'll give you a little bit of hints. First of all, this one here, you can double check. Please do cross check. This proof sequence here, this is sequence here, correspond to this particular proof obligation. Again, quick review. It's to do with the guard of ML out. And then it's about invariant number 1. And then it's about invariant preservation. All right? I can tell you that this one here is provable. And here I'm telling you, these are the rules you may want to consider. But don't get me wrong. In the actual written test or exam, I may not put these one for you. I may not tell you which ones might be relevant. You have to choose, right? But no way you're practicing in the class. That's okay. Okay? Why don't we try 2 of them before the break? Okay, just try 2. Okay. Let's try this one here. How do we prove it? I'll pause for a minute. You only have to choose 1 or 2, or 1 or more of the inference rule I put for you. Either ORR1 or monotonicity or decrements or P2. Okay, that's all you need. Little hints for you just before I take Diago's input. Okay, typically, when you got a number of hypotheses, may not be all of them are useful. You may just want to choose the one that's kind of useful for you. How do you judge which one might be useful? Of course, there's no general rule. It's more like a math, right? Think about which variable is being involved. Since we talk about n here, so you may want to choose at least a rule, at least a hypothesis that's to do with n, and then something else, right? Anybody? Oh, Diago, sorry. You wanted to say something, right?
Monotonicity. So we can disregard 2 of the hypotheses that are not related to the consequence.
So which one is relevant? Which hypothesis is relevant?
N belongs to natural numbers.
And then, so you basically say n is a natural number, turnstile, n plus 1 is a natural number. which rule can you apply?
Monotonicity.
Okay, once you get there, how do you continue? Let me just ask first, and I'll write it down.
Once I get there, how do I continue?
Yeah.
Then after that, you can apply P2.
P2. Okay, pretty good. What Diego said was completely right. However, I do want to point out one common mistake. What you are thinking, you might be thinking, this one here, n is a natural number. Given that is the case, n plus 1 should also be a natural number. And these two match very nicely about the P2 over here. I'll make it a little bit larger. Okay, that one is really about given n is a natural number, n plus 1 is a natural number. Exactly match, right? Now, question for you. Can I simply say this one, this whole thing here is already proved by P2? That's a question. Okay, your intuition is right, but why is that not correct? Go ahead.
Because P2, we look at the inverse rule, does not include other sequence that is not supposed to. For example, D is a natural number, P is less than D is not included. So we cannot apply this rule.
Yes, that's pretty much correct. Okay, so now if you look at P2, okay, guys, this is important. Okay, if you look at P2, we are saying that given n is a natural number, that's the only hypothesis you can have, right? But here, you not only get this, you also got others. So that's not part of the P2. So you cannot apply P2 just yet. All right? So here, I'm going to say that, right? This is actually even more important than the actual proof. Okay? Not valid. Because P2, okay, let me just be very precise. Because the consequence of P2, this is the consequence of P2, has a single hypothesis only, has exactly one hypothesis. This sequence over here has more than one hypothesis, so they don't match. If they don't match, you can apply it. Okay? So as Diego said, let's now apply monotonicity. So here I will say this is the only one that's relevant to me. And then I'm going to use these two. All right? So what I will do is I'm going to apply monotonicity over here. That one there is going to give me a smaller sequence. So I'm still trying to prove the same goal. N plus 1 is a natural number. And I'm only including this single hypothesis. That's what monotonicity allows me to do. I can drop as many hypotheses as I want. Okay. And then this one here, n natural number, and also n plus 1 natural number, and also n plus 1 natural number, now they completely match the P2. All right, so I can now do it. All right, P2. All right. So this is the proof I can do. This one here, followed by monotonicity, and followed by a smaller sequence, and then followed by P2. That's the right proof sequence. Okay? It is important for you to really understand why you cannot apply P2 directly. Okay. All right, question? All good? All right. So why don't we take a short break, and then we'll continue. Okay. We can do iClicker at the same time, please. Let's now consider another sequence. I would suggest we do all of them, just for completeness, since this is the very first time you're doing this, right? Okay, what we just showed is this guy here was provable, right? We prove it. Okay, I'll put a green one here. All right. So the idea is if we are able to prove all 4 of them, that would mean our current model, as far as the invariant preservation concerned, is correct. Okay, let's see. Okay, let me choose a sequence field because I do know which one will prove, which one will not prove, right? So let's go with this sequence here. Guys, why don't we try to prove this one here? This is provable, I can tell you. All right? But how do we prove it? Any idea? I can tell you that somehow you may want to look at somehow the decrement rule. Because if you see right here, I'll show you a little bit. I'll give you a little bit hints. If you look at decrement rule, that says that if you got n less than or equal to n, we got something kind of similar. And then we got, oh, sorry, let me say it again. Let me say it again, more precisely. This is decrement rule. And in the hypothesis, we got n less than or equal to n, n less than or equal to d. Think about a d here is like an n, precisely. However, if you look at n minus 1 less than n, not exactly, right? So you got less than, but here we got less than or equal to. So you cannot just say monotonicity and then apply decrement rule. That's not going to work. You have to play a little bit with manipulation of the rule. Okay? Okay, so this is the place. Okay, I'll take some input from you first.
Yeah, so let's divide the consequence n minus d less than equal to d into n minus 1 less than d, or n minus 1 is equal to d.
Awesome. Okay, yeah. Somehow we can use the OR, right? That's very good. Awesome. Yeah. So guys, I want to show you another very powerful rule. Okay. In some way, you can think about any kind of inference rule that you also kind of try to really prove something. If they simply don't work, but I do believe there's a proof to it, you can use something called ARI. Okay. But don't overuse it, right? Because whenever you use ARI, we have to justify, right? Okay, I'll show you too. Okay. ARI is for this course, whenever you say ARI, really mean literally arithmetic. Whenever in the exam or in the written test, if there's anything you want to somehow do some rewriting, or you believe there's some property you can prove aside and apply it, it's okay. You can just put ARI. However, especially for the exam, you cannot say you got some big thing and then say ARI and prove it, right? You cannot do it, right? So ARI is sometimes for something very small, something short. And if you do put ARI, make sure you put some justification aside, all right? So now I'm going to put some justification. So this ARI here, I'll just say whenever I got A less than or equal to B, that's the same as A less than B or A equals B. That one's obvious. If you write like a justification like that, it's satisfactory. All right. So now let's rewrite the sequence into this. So I'm just going to put something here. So sometimes, for the first rule, you can apply monotonicity or you can apply arithmetic. It's kind of up to you. But typically, these are the only two. Typically. Okay. And then let me still copy down all the hypotheses. So D is a natural number. N is a natural number. And also N less than or equal to D. And then here I got disjunction, right? Less than or equal to is split into less or equal. So I got n minus 1 less than d, or n minus 1 equals d. Okay, by arithmetic. All right. And then we got very close to the decrement rule, right? Let's look at it again. N less than or equal to n is really n less than or equal to d. However, you can see n minus 1 less than n. N minus 1 less than d is only on the left, but we've got some distraction from the right. Can we do something about it? We could, right? Remember ORR1 or ORR2, we can selectively choose which goal we want to prove. Now in this case, should we apply ORR1 or ORR2? R1, right? Because we want this guy here. We don't want this guy. All right? Now think about this proof, right? So I can now do, for example, first of all, let's do monotonicity. That one there, I just want to keep just this one here. Okay? So I only got n less than or equal to d, and then turnstile n minus 1 less than d, or n minus 1 equals d. And then I want to select this one here so that I can apply decrement rule. All right. If I select that, if I got OR R1, I will get something like this. N less than or equal to D, turnstile, N minus 1 less than D. Right? That's what I have. And that's exactly the decrement rule. N here is the N here. M here is the D here. N minus 1 less than N less than D. Right? We got complete match. Okay? So we're going to end the proof by saying it matches the decrement rule. Right? So it's really something you should put here. Right? I just didn't have space. Put the decrement there at the end. And that's it. This might be the longest proof we have done so far, right? So, which is nice. We'll see something a little bit longer, just a little bit more interesting to see the manipulation. We'll see that. All right, so these two are the provable one. Okay. However, I can tell you the other two are not provable. Okay. If they are not provable, that means we haven't got enough appropriate hypotheses to really prove the goal. In that way, for those missing hypotheses, we got choices. We should really go back to the model and try to do something about it. Question?
If we instantate P2 as an hypothesis, do we not also get P2 prime from it?
So which one? Sorry, you mean you mean this one here?
Yes. If we have that as one of our hypotheses, P2 prime. I'm saying for the top right.
This one here?
Yeah.
Mm-hmm.
No, the one to the right.
Oh, you mean this one here? Oh, yeah, this one here.
Can't you just do like a mod to make it like n is part of n?
Tell me what you want to do. Why don't we do what you're suggesting here? So if I do monotonicity, for example, so which hypothesis would you like to keep?
N is a part of the natural numbers,
Mm-hmm.
and then n minus 1 is part of the natural numbers as the n. Can't we use P2 prime for it, or is that not instantaneous with P2?
No, it's not. Okay, let's see why. But if you look at that, actually, given that n is a natural number, how can n minus 1 be a natural number? Because n is 0, 0 minus 1, right? So there's no P2 prime. I don't think so. So let's see, okay, just to see. P2 prime over here is different, okay? So here we say that n should be strictly larger than 0, right? Just be careful, right? So the P2 prime you're talking about, given that n is strictly larger than 0, then n minus 1 is a natural number. But what we are seeing over there is actually this. We're seeing that n is a natural number, meaning that n is larger than or equal to 0. There's an equality there that we are including. So this is not right. See my point? Yeah, good. Okay, awesome. So guys, I think your fellow student is pointing out some interesting proof, but just not the way to really go. So if you simply apply, say, P2 prime, no, it's not valid.
Even just besides the hypotheses, if we do add, or besides that theory, just like in general, like a general rule, if we instantate P2, do we also get P2? Are we also allowed to use P2 prime as like a hypothesis?
I don't quite follow you. Can you say it again? Maybe after class, okay, and then we'll talk about it. Yeah, thank you. All right, let's now, let me wipe this out, and then let's try something here. So sometimes when you actually get to a certain point that you kind of get stuck, that you cannot continue any further, that will give you some insights about what's missing, okay? I think that's the main point. Let me just erase it, okay? Just this one here, okay? Oh, sorry, right here. Let me now, first of all, let's do some monotonicity. So I will start with monotonicity. And since we are talking about n minus 1, I think I'll do something very similar to what your fellow student just suggested. I think this will be relevant, right? Since we are actually talking about n itself. So here, n is a natural number. N minus 1 is a natural number. Okay, let's say if I have that. At the moment, we say that this particular sequence here is unprovable at the moment. Unprovable. Because, for example, if n is equal to 0, then n minus 1 is not a natural number anymore, right? It's an easy witness to really show. All right? But wouldn't it be nice if we can add some new hypothesis over here? For example, if we are able to add one more hypothesis right here. And then you may be thinking, how about we just say n is actually larger than 0? Not only that it's a natural number, but it's positive. In that way, after adding this extra hypothesis, we will be able to prove it. We will be able to. Now, here's a question. What does it really mean by adding this hypothesis? Okay, or maybe I'll just go directly, all right? So guys, let's talk about this one here. It is very important for you to see the flow, right? Otherwise, you might just get lost in the whole discussion here, okay? First of all, we know that this original sequence we want to prove. This one, first of all, correspond to, let's get a big picture right, MLN slash invariance 0, 1 invariant preservation. All right. Let me also bring the rule very quickly, okay, and then we'll talk about it. Because later, whenever we encounter any similar unprovable sequence, we're going to use the same reasoning. Okay, so let me just copy this one here. So that's a rule. Okay, let me copy that. All right, right here. Right here. So remember, this one here comes from this, and let's remind ourselves very quickly. This one here is the axiom. And this one here, both of them. These two are the invariants in the pre-states. There's an implicit true, which is a guard for MLN, right? So you can think about, I can also write it down, okay? You can think about this really some implicit true over here, and the true there correspond to the guard for MLN. And this part over here, n minus 1, is the, if you remember MLN, the action has n prime equals n minus 1, right? n minus 1 really come from there, right? Is this. Okay? That's something we did earlier. The reason that we had to prove this sequence is because we got this proof obligation rule and the model that we're given, right? So now, if I want to add, so given that this sequence is unprovable, we may want to add some additional hypothesis to help, okay? And the additional hypothesis that we are talking about is this one here, n larger than 0, all right? Now here's a question. If I want to add n larger than 0, where should I add n larger than 0 back to the model so that when I regenerate the sequence, it's going to be there? Okay, so here's a question. Where should this hypothesis go? In the model. Okay, we got choices. Choice number 1, we can add a single axiom to say n larger than 0. That means n is always larger than 0. Okay? But is that true? Cannot be. N could be 0, right? In the very beginning of the system, n is simply equal to 0, just empty, right? So this is not the way to go. Or we can add some invariance, additional invariant to say n larger than 0 is an invariance. That one also wouldn't work. Invariant also must be true always. N cannot be true, like a larger than 0 always. N can be 0, right? So the only place that's suitable for us to add is this. So this is the only suitable place. This is the only suitable place to add the extra hypothesis, which means we're going to add an extra guard to the MLN, since we're talking about MLN. So MLN, the events, is going to have the guard when n larger than 0. And then the action will just be the same as before. So that's what you will see in the final model. Okay? So this is some extra guard. And once you add in this extra guard into the events, when you try to regenerate the proof obligation, n larger than 0 will be there. Okay? Let me recap what's going on here. It's quite a bit of detail here. Let's think about what's, let me just add one more flow chart over here. I think that will help. Okay? And then let's now do that quickly. Just give me one moment. Let me just find out the diagram I have in my notes. There we go. All right, I'll revisit this page in just one moment. Okay? Let's think about what's happening here. What we have is some model, M0, right? Initial model. We know that we got static, we got dynamic part. We got static part. We also have dynamic part. Right? We got variables, we got constant, we got axiom, we got invariant, etc. Right? And then, given a particular proof obligation rule, for example, the invariant rule, invariant preservation. All right? We're going to generate a series of sequence. We're going to get, for example, ML out, invariance 0, 1, invariance, all the way to ML in, invariance 0, 2, and then invariance. We know that we got 4 of them. Right? That's what we said earlier. So we got 4 sequence to prove. And then the next step, which is what we just did, we try to prove them. And then we'll attempt to prove. And you might have some sequence that's unprovable. For example, the one we just saw, I'm going to come back here. This one here was unprovable. This one here, right? ML in 1. So for example, let's say if ML in invariance 0, 1, unprovable. That's where we are, all right? What should we do usually in the big picture? The way to do it is you have to go back to your model and fix it. It's a little like running JUnit test cases. If you get a red bar, something wrong with your code. Go back to your code, fix it, rerun the JUnit test cases. Similar. If you have something unprovable, go back to the model, fix it, regenerate all the proof obligation, try to prove it again. Similar. All right. So here, once you got anything that's unprovable, what you do is you got to fix the model. Okay. In this case, the way we fix it is by add an extra guard to MLN. So in the case of MLN, if you look at the revised model, I'll show to you later. We have when it's got this n larger than 0. So now we basically got M0 prime in the sense that it's been revised. So once this model is revised, what should we do? Regenerate all the proof sequence again. So now after it's regenerated, all the proof sequence over here will have that extra hypothesis, simply because we have added one extra guard to the MLN. Question?
Does it always have to be a guard, or can it be?
Very good question. If you don't mind, I just interrupted you, right? Your fellow student question was, should the extra hypothesis always come from an event guard? Not necessarily, okay? So you should really try to compare these two pages together. So here we're saying, if there's anything that's unprovable, you should really go back to the model and fix it. All right, so now, where should we fix it? Let's go back to the rule over here. Because the rule is going to generate a sequence based on axiom, invariance, guard, these three things. So these are the three possible sources you can modify. I know that the extra hypothesis I want is n larger than 0. I can either try to add n larger than 0 as a new axiom, which we know should not be the case. We can also try to add it as a new invariance, which should not be the case. N could be 0, really. So the only place left will be add an extra guard for MLN. In this case, it makes sense. You should only let the car go back to the mainland when you got at least one car there, right?
When should you add something as an axiom compared to something as an invariant?
Good question. In this case, axioms are defined in terms of constants. Invariants are defined in terms of variables. So actually in this case, n larger than 0 should not even go to axiom because n is a variable. It's not even a constant, right? So that's not applicable right away, all right? All right, let's now recap. Okay, I think well, let me recap, and then we'll do one more, and then that'll be it for today. Let's think about what we're doing here. We try to prove this particular sequence over here, and then we find that it's not provable. To really make it provable, we find that we really need this extra hypothesis and insert it over here. Mathematically, yes. But the value about this course is not just to look at the sequence literally. We want to think about where this sequence comes from. The sequence here comes from a model that we specify for some system, right? So now if we find that one of the sequence generated by the model is unprovable, naturally we should go back to the model, fix it, adding hypothesis somewhere, and regenerate the proof sequence. So then we can prove it, right? So the model here is really the source for us to generate all the sequence according to the proof obligation rule. Now, also your fellow student pointed out, when should you do axiom, when should you do invariance? If the extra constraint or hypothesis you want to add has to do with constant only, you may want to consider either axiom or guard. If the extra hypothesis you want to add involves variable only, in that case, you may want to consider invariance or the guard. So guard is always a candidate. Whether or not you should really go for invariance or guard is kind of you got to judge. But the reason that n larger than 0 should not be an invariant in this case is because n larger than 0 not necessarily have to be true always. Because in the beginning of the system, n would be just 0, which can violate this invariant right away. So it's not a good candidate. Okay. All right, subtle, but make sure you grasp it. All right. And question about this diagram here? Okay. All right, guys, think about the issue, right? Let's now do one more, and then we're done. How about this one here? This one here is also unprovable, I can tell you. Okay, why don't we just do it for completeness, and then we'll continue on Thursday. Okay, bear with me, just about 1 minute or two. Okay, for this one here, I would suggest we look at n plus 1 less than or equal to d. Somehow they involve both the variable and the constant, right? So in this case, let's say we believe this one here is relevant to us. Let's say, well, let me use a different color. There's one here, and also there's one here. This one you were almost there actually, right? So let's say monotonicity. We have n less than or equal to d, turnstile, n plus 1 less than or equal to d. This one here, not exactly provable, right? It's not provable. Okay, I'll put it here. Not provable. For example, if n is exactly equal to d, in that case, if you say n plus 1, it will be larger than d. Cannot be less than or equal to, right? If I want to add some extra hypothesis, what would be my choice? Right? In this case, I can tell you. So this is symmetric. Before, this extra hypothesis will add to the guard for ML in. It turns out this new hypothesis we're going to get will add to the guard for ML out. Because whenever you want to actually have some card going out, you want to make sure it's also capped. Okay? That one I can revisit when I do the recap. So this one here, we're just going to want to add n less than d. Okay, right here. So this is some extra hypothesis needed to prove. And again, we got three choices. Should we add it back as an axiom? Should we add it back as invariance? Should we add it back as the guard for ML out? Three choices. Choice number 1 cannot be axiom because n here is a variable. Axiom should only involve constant. Number 2, we also get about the how about the invariance? Should n always less than d? Not really. It can be exactly equal to d, right? When you reach the maximum, right? So invariant and axiom, they're not applicable. So in this case, we should really add a guard to ML out to say when you got exactly, you can only try to increment one more card into the island bridge compound if you are strictly below the limits. All right. So this is the kind of interpretation we want to keep exercising. All right, I would say I'll stop here. Okay, we are basically through. So I would say when we come back on Thursday, I'll try to recap again about everything, and then we'll continue with it. Thank you.